Hey everyone, thanks for coming in. We have Michael Walter here from the University of Amsterdam and all these other lovely affiliations to tell us about, give us the second talk on the hidden symmetries part of the bootcamp. So take it away, Michael.
Great, thanks a lot, Cole. Is the audio okay for everyone?
Yes.
Thanks, great. Yeah, thanks everyone. Thanks to the organizers for inviting me to give, I guess, part two of this lecture series with Avi. Yeah, and apologies that I couldn't make it in person. Surprisingly, participating in a boot camp did not appear to warrant a national interest exemption or exception to fly over. So that's how things are currently. Anyways, I'm very happy to give this talk. I mean, it's about sort of a line of work that really has been developing in very interesting ways over the past years, and so let's jump right into it. So here's a recap of parts of part one of Avi's talk. And so basically he showed us one algorithm, two classes of problems, and then at the end were three questions, and we want to try to address those questions in this lecture. So the algorithm he discussed, right, was alternating minimization, sort of a meta algorithm that he would apply to different problems. And generally, he spoke about two classes of problems, right? The first one were what we call scaling problems, in particular matrix scaling, right? Scaling a matrix by row and column, rescalings to be doubly stochastic. Operator scaling was sort of this quantum version. Tensor scaling, I think it was maybe mentioned at the end, maybe not in great detail, but that also exists. So these are problems where you have a mathematical object, you want to transform it in a way such that it looks uniform in some sense. For example, in the sense of being a doubly stochastic matrix. On the other hand, in the last 10 or 15 minutes or so of his talk, he also discussed a seemingly different field, invariant theory. Yes, invariants flowing around, group actions are protagonists. And there was one very basic problem to which alternating minimization also applied, and this was the problem of NALCON membership in the NALCON, which could be phrased in the language of invariance, or in a more analytical language, namely as asking whether for a given vector, whether the orbit's closure contains a zero vector. In other words, can I sort of squish the norm of my vector? Can I make the norm of my vector as small as I want by applying the group action? And key to the analysis of these algorithms turned out to be, or it was sort of slowly revealed, that really what's happening is that these algorithms, they move inside a group, in this case, a group with product structure, hence alternating minimization applied. And that invariant quantities were key to the analysis in one way or another. For example, the permanent, while not being strictly left invariant, it does in fact the potential function from the perspective of the first analysis. It transforms in a very controlled way. Sometimes that that might be called a semi-invariant. I guess then maybe some things we didn't get to talk about in the end. It turns out that invariant theory more generally also provides powerful tools to analyze the second application, named this NALCON, the application to the NALCON problem, basically by giving us good bounds on various quantities. And I hope this will be clear later in the talk. So that's sort of a recap, and then the three questions that we were left with were the following. The first one, of course, was why should such a simple greedy algorithm work? I mean, greedy algorithms usually work if there's additional structure. Now it has, of course, already been mentioned several times that this structure will be a kind of convexity. It will be geodesic convexity. So that's something we would like to see more clearly. The other question, is why are these? What's the deal? What's the relationship between scaling problems and this, somewhat esoteric or technical, if you're not an invariant theorist, an NALCON problem? Okay. So there is a deep connection. I would like to explain what it is later in the talk. And then, of course, one reason why you might want to ask these two questions is so that you can also tackle the third one, namely going beyond multilinear actions of product groups, right? Because only for those is it easy to solve these sub-problems in an alternating minimization scheme. And here's two examples where alternating minimization might not obviously apply, even though there's maybe perhaps caveats that we could discuss. So one is simultaneous conjugation. So it's like the left-right action, but you use the same group from the left as from the right. So you do like G times AI times G inverse. There's only one factor now. So somehow if you had an alternating minimization scheme, you would have to, there's a single GLN. So you would have to sort of solve the problem in one step. So that clearly, we can do. Another example would be if you want to scale symmetric tensors while keeping the symmetry. So you would have a tensor and you would, again, scale by G, tensor G, and so on. If you did alternating minimization, the fact that you alternate between the tensor factors would destroy the symmetry of the tensor. So these are just two examples why alternating minimization really isn't good enough. So that's sort of the starting point for this talk. And what I want to discuss indeed is maybe give you sort of a high level overview of where we want to go and what the connections are, and then really setting the stage for what will come, zooming in. Then I want to sort of motivate why, what is this kind of convexity that we talk about? It will turn out that if the group is commutative, we'll talk about ordinary Euclidean convexity, whereas if the group is not commutative, we'll talk about GDZ convexity. Then somehow there's this duality statement, which really explain the equivalence between scaling, NALCON, and another problem that I guess we've already heard, the problem of minimizing norms, L2 norms. And once we understand those structural ingredients, it will then be very easy to formulate algorithms, not so easy to analyze those. So we won't, I'll only sketch this. And if time permits, we'll also talk about polytopes. We mentioned polytopes. It turns out that it's maybe not surprising that in a Euclidean convex setting, convex polytopes might appear. It turns out they even appear in this geodesic convex setting where there's no obvious Euclidean convexity around. And it would be nice to have, maybe we'll have a few minutes to discuss that as well. All right, so that's the plan. And let me start with the big picture that sort of, shows all the protagonists in this game. So this is the NALCON problem, as it was one way of stating it. That's sort of the analytical way of stating it, if you want. We're asking, given a vector, here's its orbit, right? We move along by the group action. There's an orbit. We can close this orbit. And now we're asking, is 0 in that closure or not? So here, it would not be, in general, let's say, problem that we might want to decide. Okay. For example, we might want to decide this because we are invariant theorists. So we like actually algebra, and we want to ask an algebraic problem, which is equivalent to this one. And that's also something that Avi mentioned. That was actually his first definition of NALCON. So NALCON turns out to be exactly, so a vector V turns out to be in the NALCON exactly if it's indistinguishable from the all zeros vector by any invariant polynomial. Okay. So if no invariant polynomial can tell apart our vector from the zero vector, then and only then it is in the NALCON. Okay. So that's a pretty algebraic question, right? It seems to involve a for all quantifier. It turns out these invariant rings are finely generated, but that's not an efficient way of going about solving this problem. So we are looking for new ways. Okay. And this new way, of course, is by treating this, by looking at this formulation and thinking about it as an optimization problem. So really what we want to do here is we want to imagine we start with a vector V, and then we just try to minimize its norm, staying inside the orbit. And if we can push this norm all the way to 0, then we're in the NALCON, otherwise we can't. So this leads us to tackling this NALCON problem by a minimization, or phrasing it as in terms of minimization problem. Tackling it by solving a possibly harder problem, a minimization problem, which is minimizing the norm of G dot V. So this is the group action applied to this vector. The norm is always L2 norm in my talk over this group. Okay. Now, whenever we're faced with a minimization problem, the first thing you might want to do is look at critical points. Let's say necessary condition for minimality. So we might also want to do this here. So what we could do is we could say, well, okay, clearly one necessary condition for being at a minimum is that the gradient of this objective function as a function of G, right, of the group element, which we use to move along the orbit, is equal to 0 for a minimum or close to 0 for an approximate minimizer. So we might want to discuss what this gradient means. I think maybe on Monday it was already explained. So that's maybe already clear, but we'll come back to it concretely in a moment. It turns out that we might therefore want to start attacking this problem, and therefore the NALCON problem, actually studying this one, the problem of basically minimizing gradients. Now, there's two magical things that happen. The first magical thing is that these gradients, they have sort of their own relevance, as we'll see in examples, in 3 examples at least. It turns out that these gradients exactly, they do, as concrete and useful things as computing row and column sums, computing marginals of quantum operators, and doing all other kinds of marginalization procedures. So setting the gradient to 0 is not just a sort of a technical tool, and sort of if you have the larger dream of minimizing a norm, but it's actually often the problem of prime interest. So we can think of this problem of minimizing gradients actually as a very general scaling problem, and we'll see how it materializes, say, for matrices in a moment. Now that's the first magical thing. We actually care about this problem of minimizing the gradient, so we give it a name. We call it the scaling problem. And later we'll also give this gradient a name. We will call it the moment map. The other magical thing is that actually minimizing the gradient is going to be equivalent to minimizing the norm. And that follows by a geodesic convexity property. Okay. And so that gives us sort of the panorama. And in the following, we want to zoom into this more. There's also a last connection. I mentioned that this gradient will do things like computing row and column sums. Now it's an interesting problem to make row and column sums uniform, let's say. But more generally, we might want to scale our matrix to general marginals. And we could ask, what are all the possible marginals that we can scale a matrix to? It turns out that's one way in which polytopes appear, namely the set of possible marginals R, C, to which we could scale a matrix, and analogous statements and very large in height and very large generality actually form convex polytopes. Okay, and so that's sort of explaining this picture in more detail is sort of the ambition for the next 50 minutes. All right. So let's start slowly and let's just recap our setting. And I'll try to be concrete to the sort of, with the danger of being cartoonish. And you might think that, this whole theory only applies to GLN. GLN is very, important example. And, more generally, we look at things like, SLN, determinant one invertible matrices, or what's called an N-torus. So that's, say, diagonal N by N matrices, or, just N tuples of numbers, which form a group just by component-wise multiplication. Or what I'm not sure what might have appeared in Avi's talk, STN, which is determinant one diagonal matrices, N by N diagonal matrices. So these are the kind of groups and maybe products of those that we'll care about in this talk, but the whole theory generalizes to a setting that we might have time to mention, or we might not, and then we could discuss it after the talk. So suppose we have such a group and it acts on a finite dimensional vector space by linear transformations in a reasonable way. Then, with this data come orbits. So that's the set of all vectors you can obtain from a fixed vector V by applying the group action, and orbit closures, as you saw in the last talk. Here's a simple example, a C star. So just a non-zero complex numbers act on two-dimensional complex vector space C2 by multiplying by G in the first component and by G inverse in the second component. What did the orbits look like? Well, clearly the product of X and Y is invariant under this action. So that gives us, generic orbits where X, Y equals some constant. For example, here, X times Y equals 1 would be this blue hypersurface, or it's a projection to the real to R2 here, or its intersection with R2. But there's also other orbits, right? So this blue orbit would be a closed one. But this green orbit, the horizontal axis without the origin turns out to also be an orbit. It's the orbit of 1, 0. And it's not closed, right? Because it contains 0 in its closure. So the 0.10 would be an example of something in the NALCON. The 0.11 or any two non-zero coordinates would be something that is not in the NALCON. Okay. So now we discussed we want to tackle this NALCON problem by studying, by minimizing norms. And so let's give this protagonist a name. So let's denote the minimum L2 norm in the closure of an orbit through vector V. Let's call this the capacity and denote it by cap. Okay, so cap of a vector in such a general setting is just the infimum of the norm as we move along the orbit, or the minimum of the norm as we move along the orbit closure. Okay, and that's the basic optimization problem that we want to solve. And it turns out that it does actually, up to some mild, taking powers or nth roots and so on. It actually coincides with matrix capacity, which I'm not sure was mentioned, polynomial capacity, and operator capacity, so Gervitz's capacity. So they're basically the same thing in disguise, but it's not obvious from the formulation. Okay, so that's the thing we want to compute or approximate, our basic optimization problem, our primal problem, if you wish. So to get a sort of a feeling for this, I want to look first at commutative groups. Again, those are usually called tori, so I drew a torus. It's maybe not clear why they're called tori at this point. And let's actually revisit, matrix scaling from this mindset. I think maybe this also addresses some questions that were there before. Should we look at complex matrices? Should we look at matrices with positive entries, L2 norm, L1 norm? All right. So here I want to set it up in the complex setting. So my group will be two pairs of n by n diagonal matrices, invertible diagonal matrices. So Tn times Tn. And I want to act on complex n by n matrices by scaling the rows by the G's and the columns by the H's, right? So that's the group action that we want to study. Now we could ask, what is capacity here? So what's the minimum norm? Let's try to find an expression for this. So let's look at the norm square because that's nicer, right? Norm square would be just sum of the squares of the entries. Well, we are rescaling the rows by the G's, the columns by the H's. So that's simply the sum of squares. That's sum of Ij, absolute value Gi, Mij, Hj, absolute value squared. Now, if you were to carry out this optimization problem, the first thing you would notice is that we don't need the richness of the complex numbers because we anyways taking the absolute value squared. So we could make a change of variables, right? And we could say, well, absolute value of gi squared, we'll just call e to the xi. And similarly, absolute value hj squared, we call e to the yj. And so we then arrive at this reformulation here in phi of x, y, which are now real vectors. They are the exponents of these e to the xi's, e to the yj's. And we arrive at this function, and minimizing this function is completely equivalent to computing this capacity squared. Okay, so that's just this L2 norm in this case. So it turns out that this function, sum of exponentials, is convex in x and y. It's even log convex, and what we're doing here is really an easy example of a geometric program, right? So that's nice, right? So there's convexity after a very simple chain of variables. We just write our group as e to the x, and then it's convex in x. So that's nice. Now let's take one other step, and you should not tell me at this point that this implement is 0, although that's the case. Let's take another step and compute gradients. Okay, so what's the gradient? Well, let's compute the gradient at x equals y equals 0, because we kind of want to know, is our matrix already minimizing the norm? Well, if you do so clearly, if we take derivatives with respect to the xi's, right, we're summing over the j's. If we take derivatives with respect to the yj's, we're summing over the x's. So what's happening here is that the gradient is simply computing row and column sums. And if we compute the logarithmic gradient, we are going to get normalized row and column sums, or in other words, row and column sums of the matrix whose entries are absolute value squared of mij divided by the whole Frobenius squared. Okay. So this is, of course, in matrix now with non-negative entries. So that's how the transition from complex matrices to matrices with non-negative entries happens, where L2 norms get translated now into L1 norms. Okay, L1 norm after taking squares. Okay, so that's great. Okay, now we do one small modification, and then this technical slide is done. The modification we do is instead of looking, so why do I want to do a modification? Okay, so first of all, it's great that our gradient computes row and column sums. So it confirms what I asserted before, that we like gradients. We like gradients of norm squares. Unfortunately, we don't want to set this gradient to 0, but we rather want to make it uniform if we want to scale to doubly stochastic matrices. So we have to modify the group in such a way that we get a condition for uniform scaling, for doubly stochastic scaling, and not for making the matrix 0. And that can be done simply by imposing the condition that these diagonal matrices here should have determinant 1s. We call this STn. So what happens then? Well, the thing that changes is that now if we make the same change variables as before, now the components of x and of y have to sum to 0. Okay. So in other words, like the traceless vectors, if you want, or sum equals 0 vectors in Rn. Okay, so it's a subspace, and hence also the gradient will live in the subspace. And what will happen is simply that we subtract, something proportional to the all ones vector to make the resulting thing traceless. And so now we're happy, right? Because setting the gradient to 0 means making the rows and column sums uniform, which means making our matrix doubly stochastic up to a factor 1/n, if you wish. Okay. So this slide, I hope, shows very concretely that, for matrix scaling, norm minimization for a natural group action and matrix scaling, the task of, making the rows and column sums uniform, are completely equivalent. And it maybe gives the first motivation why, because of this convexity, this log convexity that I mentioned here, maybe that gives the first indication why Synchron, a simple greedy algorithm like Synchron should solve these problems. Well, so both of these problems. And in fact, I mean, the idea that one should use this potential function or the logarithm or slight variant of it is the starting point for cutting edge algorithms for matrix scaling that achieve better guarantees than Synchron. So that's what I wanted to say about matrix scaling. All right. Now I want to do one more example. It will look very similar. I mean, so I'll be a bit quick, but it's interesting because it's some sense generic. So the next example I want to look at is I want to look again at this time only n by n diagonal matrices, not a pair, but a single n by n diagonal matrix, a group of n by n diagonal matrices, centaurs, acting on Laurent polynomials and n variables. Okay, so Laurent polynomial is a polynomial where the exponents are allowed to be integers, not natural numbers. And I use this notation z to the omega for z1 to the omega 1, z2 to the omega 2, and so on. So omega is an exponent vector here. Okay. And the way the group acts is simply, well, it's just rescaling, monomial in the obvious way. So z1s get rescaled by g1, z2s by g2, and so on and so forth. Okay. As before, we can compute capacity, which is the norm square of such a polynomial. The minimum norm square as we apply group elements g. And so, well, the norm absolute value square of these coefficients, what is p omega absolute value square, g omega absolute value square. We make the same change of coordinates, e to the x. We call this e to the x. sorry, we call G absolute value the entries of this group element G absolute value squared, we call e to the x. And now, well, this expression here then simply becomes e to the x dot omega, right? Where omega is, again, one of these exponent vectors, and x is an arbitrary real vector. So same change of variables as before. For the same reason, well, again, this is a geometric program, so it's going to be log convex in this variable x. And so that's nice. Okay, so what do we learn from this? So here's a simple observation. When is this capacity equal to 0? So when can I make this quantity as small as I want? Okay, so clearly that's possible if I can find a vector x, a direction x, that has a negative inner product with all of these omegas. Okay, so now, and it turns out that's the case if and only if I can find such x. In other words, x is sort of determining a hyperplane that separates the origin from the convex hull of these weights omega. Okay. So that means that capacity is 0 if and only if 0 is not in the convex hull of these exponent vectors that actually appear in the polytope. Equivalently, capacity is positive if and only if this point 0 is in this convex hull of exponent vectors, and that's exactly what's called the Newton polytope. Okay. So we see again for this very simple group action, there's interesting things happening. There's an interesting geometric program generalizing matrix scaling. There's polytopes appearing here. It's a standard definition Newton polytope of a polynomial, Laurent polynomial. And again, we can compute the gradient by similar reasoning as before. The logarithmic gradient at x equals 0. Well, we'll just pull down, right, these omegas. So we get, a sum over p omega squared omega divided by sum of squares. So that's a convex combination, right, of these exponent vectors omega that appear. So clearly this gradient is a point in this Newton polytope of the polynomial. And it turns out, it's not completely obvious, but true, that as we move along the group orbit, these gradients actually sweep out the entire polytope up to some closure. Okay, so this polytope in some sense is implicitly described by gradients of a Laurent polynomial. Okay. And so the reason why I want to show you this example is because it's essentially universal for commutative group actions in our setting. So any nice commutative matrix group of the form we'll consider, any reductive such group, is essentially an n by n torus up to some change of variables. So really, Laurent polynomial and any representation of such an n by n torus is essentially similar to an action on Laurent polynomials. If you know why I'm lying, you also know why maybe it's okay to lie here. So point is that, okay, there's convexity. It's revealed after change of variables, okay, basically going from R plus to R. And it already gives a bunch of interesting examples, including matrix scaling, right? And somehow recognizing this geometry, this convex geometry, which is actually a simple example of a geodesic convex geometry, is sort of key to actually cutting edge algorithms. All right, so that's a commutative situation. So now we want to continue and ask about the non-commutative setting. So what should we do there? And what I want to do is just sort of proceed by analogy and see what happens. So again, the function we want to minimize is the norm or norm square, or I will actually take the log norm. The log norm has the advantage that this objective function is bounded from below if and only if capacity is positive, right? If and only if our vector is not the NALCON. So in some sense, this problem is feasible if you want. Exactly if you're not in a NALCON. But you can also just think of it as a technical thing, or you could say it's motivated by the fact that in our commutative examples, even the logarithm of the norms was convex, right? So maybe the same is true non-commutative. So to get a handle on the non-commutative situation, let's look at the simplest group, GLN, simplest group in our setting, GLN. Now, any general linear matrix has a polatic position, meaning you can write it as a unitary times a positive definite matrix. And it's reasonable to assume, and we can always in our setting assume that actually the unitary group acts unitarily, meaning it actually does not change this norm. Okay. In this case, we can restrict the optimization from GLN to, if you want, GLN modulo UN, or more concretely to the positive definite matrices. So instead of looking at the whole group, we only look at the positive definite elements in the group. So here, any such element, of course, we can write as e to the x, where x is Hermitian, right? That's in complete analogy to what I did before. Before we had, positive real numbers as the only relevant part of c to the n, or c star to the n. And then positive real numbers we wrote as e to the x for a real vector x. And now we do the same non-commutatively, so we take Hermitian matrices instead of real numbers. Okay. So after those change of variables, now we can take a naive gradient, and we could, say, okay, that's probably the right notion of a gradient that will give us this first order condition, right? So that would be complete analogy to what I did before, right? Before I always computed the gradient of the logarithm of the norm square, or logarithm of the norm at x equals 0. Okay, so I could do the same. Let's take this log norm e to the x. Now this is matrix exponential of a matrix, which matrix x. Let's take the gradient x equals 0. That's right. Hermitian matrices are a real vector space, so that will give me a Hermitian n by n matrix as a gradient. Okay, so that's sort of the pedestrian definition, if you want. Now, the only thing I'm doing here, which I want to emphasize, is I'm changing perspective a little bit. Instead of thinking of, if I thought of this, if I computed the gradient here, I would ask, what's the base point? What I want to do is I want to always fix the base point, the point at which I take the gradient to be the identity element of the group, or the x equals 0 vector, right? Because e to the 0 is identity. But what I want to do is I want to allow this point that defines the orbit to move. Okay, and so if the function defined in this way, so the function mu that sends a non-zero vector to the gradient of the log norm function around the identity, right? So that's really saying, what is this thing doing? It's a gradient, sort of pointing to where the log norm changes in the vicinity of this vector v, if you stay in the orbit. This thing is called the moment map. Okay, and I gave you the pedestrian definition. I could have also said, the positive definite matrices, they have a natural Riemannian geometry. We discussed them, I think, Monday, and so we can just take a Riemannian gradient, at the identity element of the positive definite matrices of our objective function f. Okay, so it's a Riemannian gradient at the identity. So how does my vector, how does the norm change as I move along the orbit as a function of the space point here? Okay. Okay, so it's a bit of a mouthful, this definition, but it's really analogous to what I computed in the case of matrix scaling and the case of Laurent polynomials. Now, where does this name moment or momentum map come from? It comes from physics, right? It turns out, so it originated in Hamiltonian mechanics and classical mechanics, where it turns out that symmetries sort of give rise to conserved quantities by Noether's theorem, and things like linear momentum, angular momentum, and so forth are special cases of this construction. Okay, but it's sort of more generally, but then I guess this appeared in physics, that have been sort of abstracted in mathematics in the setting of symplectic geometry, and I imagine we'll hear more about this in the next two lectures by Nishit and Jonathan. Okay. Now, why do we care? Okay, so before we saw that this gradient, this logarithmic gradient, computed interesting things like row and column sums, or points in a Newton polytope. It turns out that in great generality, in all the examples that Avi mentioned, or would have mentioned if you had had more time, or two more lectures, this gradient captures interesting information. And setting the gradient to 0, which I here just want to say as setting mu to 0, which I here denote by setting mu to 0. This captures natural scaling problems. And if the group is non-commutative, it's going to be non-commutative scaling problems like operator scaling. The story I told you here is for GLN, right? And how did the group enter? Well, any positive definite element in GLN I can write as e to the x for Hermitian matrix x. How about products? Well, we just take tuples of Hermitian matrices. How about things like SLN? Well, to get a determinant 1 positive definite matrix, I want to exponentiate a traceless Hermitian matrix. So that's same story, and similar to how we subtracted an identity, multiple of the identity before. Okay, very good. So let's maybe do another, and hopefully that's the last of the painful calculations. Let's look at operator scaling. Right? So operator scaling, again, relied on a left-right action. So we have 2 copies of GLN, 2 pairs of invertible matrices, acting on d tuples of n by n complex matrices. So here, everything, even in Avi's talk, was complex. We don't have to do some crazy taking absolute value squared. And the action is what's called the left-right action. So GH acts on a tuple of matrices, a d tuple of matrices, by multiplying all of these matrices from the left by G and from the right by H. I take H inverse to get a nice group action, but it doesn't really matter. You could take transpose, you could take H, not worry. Okay. Now, what's the norm, okay, of such a matrix tuple as we apply a group element? So the norm, right? Again, we take L2 norm for matrices. That means Frobenius norm. And if a tuple be just the norm squared of such a tuple is simply the sum of squared of the individual Frobenius norms. If we write this out, right, we have trace of this thing star times trace of this thing, and we can again make a change of variables. Just like we said, we indicated before, and we can see now that G star G we can write as e to the x, and H star H we can write as e to the y, and so we get this expression. And maybe there's a factor of 2 off from relative to the previous slide, but I hope that's okay. So I'm doing the same change of variables as I did before, and now with matrices, summation matrices instead of real vectors, and I get this nice objective function here, right? And I can compute the gradient, and now we use this fancy word, we call it the moment map. Okay, so the moment map at point M is the gradient of this function at x equals y equals 0. How does this norm square change in the vicinity of M as we move along the orbit? Okay, we're going to take a logarithmic gradient, so it's going to be normalized by the norm 1 over the L2 norm squared. But the crucial point, of course, if I take this gradient with respect to x, at x equals y equals 0, then this thing is just an identity matrix, so it vanishes, and x just is pulled down, right, by taking the derivative. So what I get is is exactly sum over I mi star. Star is the Hermitian conjugate. Likewise, the component, the y component of the gradient will be negative because of the minus here. Sum over I mi star mi. Okay, and that's because of you use x is 0, so this vanishes, and you use simplicity to move the mi over. Okay, and that's exactly this weird sum of squares, but in Avi's notion of what it means to scale an operator, a quantum operator, okay, a quantum channel, a completely positive map. Okay, and again we can restrict to SLN times SLN, which will mean that we look at traceless Hermitian matrices. So we'll subtract the tracial part here, and once we have done this, then minimizing the gradient or equivalently setting the moment map to 0 is exactly captures operator scaling. Okay, so that's fantastic. It seems like norm minimization gives rise to operator scaling in a very natural way. But there's a slight challenge here, and the challenge or the catch is that actually this objective function here is not a convex function of x and y in the usual Euclidean sense. Okay, and that's where we have to be a little bit careful. So it's not convex. Nevertheless, two talks have claimed that these minimizing the norm and minimizing the gradients are equivalent problems. So we have to change the geometry. We're looking at it wrong. We should look at the Euclidean geometry. And it turns out that that's indeed what's going on. So why does the equivalence that has been asserted between norm minimization and scaling, why does it hold? It holds because our objective function, restricted to the positive definite matrices, like I'm doing here, is convex along curves of the form e to the xt for any fixed x, right? So rather than looking at convexity, on all the Hermitian matrices, I'm looking at these curves through the identity matrix. Okay, and these are indeed geodesics or natural Riemannian metric on PDN. Okay, so f, in other words, is a geodesic convex function. Okay, and I guess here was a little picture of what such a curve looks like. Sadly, this a should have been an x. I apologize for not updating this. But that's the situation. Okay, so we still have these curves e to the xt. We are convex along those. And what's nice is that clearly I can get from the identity to any positive definite matrix by such a curve, right? Because I can write any positive definite matrix e to the x. So clearly they're connected to the identity. And so this connectedness, the fact that any 2 points are connected, in fact, by unique geodesic, makes the theory work really nicely, almost as nice as in the Euclidean case. So why does this geodesic convexity hold? I mean, one way of seeing this is to do a calculation. Here's sort of a more abstract argument that's basically correct, and basically I'm not lying. And the idea is that, well, we want to restrict to such a curve e to the xt, where x is fixed and t is some parameter. Okay. Now, such a curve is also a commutative subgroup, right? And I kind of told you that any commutative subgroup is kind of like a torus, right? So here it would be a one-dimensional one. I'm lying a little bit, but again, that's okay. So for nice x, that would be the case. In general, e to the xt will generate some torus. Okay. But we know that in the commutative case, right? In this commutative case, any action is equivalent, I told you, to Laurent polynomials. And for Laurent polynomials, we know that if we minimize a norm square, that we get a geometric program which is log convex. So it follows at once that this log norm, even in non-commutative setting, is geodesic convex, because that geodesic convexity simply translates into convexity whenever we look at commutative subgroups. Okay, such as the one generated by e to the xt. Okay. Now Euclidean, now geodesic convexity we learned earlier this week is nice, right? For example, here, because of everything is connected by unique geodesics and so on, we can really compare any 2 points. It's not like different connected components or anything. Critical points, therefore, are not only are global minima critical points, but also the converse is true. In other words, if you have a vector that's has the smallest norm in its orbit, in other words, its norm equals its capacity. Capacity is the smallest norm in the orbit closure. Then and only then is the gradient at this point 0, and the gradient at this point, right, is exactly what we call the moment map mu of v. So in this sense, norm minimization and scaling are equivalent. It's a very rigid kind of sense, right? Because I have strict equalities here, and that's something we'll have to fix. But sort of, it gives a first glance where things should be okay. Maybe we'll be okay. No. Now, if one wants, yep.
Let me know if you can hear me. If not, I can grab the microphone. I just was curious. So is the notion of gradients you're working with here, it's the same gradient as you were working with before. It's not the one induced by this Riemannian structure where you get the convexity?
It's the same. It's the same. I mean, there's e to the x, right? It changes basically. I mean, e to the x is kind of normal coordinates around the identity. So taking this naive gradient at x equals 0 is the same as the Riemannian gradient with respect to this nice, Riemannian metric. That's not the Euclidean metric on PDN.
Oh, okay, so the gradients coincide.
Yeah.
Thank you.
Thanks. Yeah, so it's important that these curves here go through the identity, right? Otherwise, I would have like little squared of p's sitting around if I wanted to go have a different base point. Yeah. Great. So that's great. So now we have G convexity, so we can hope for nice things to happen. But if you want to make things concrete, right, we have to understand, how convex our objective function is. So, what I mean by this is that in ordinary convex optimization, there's a rich toolbox, and there's lots of function classes. There's well-conditioned functions, smooth functions, Lipschitz functions, whatnot. And right, for each of these, we know how to analyze various algorithms. So we could ask, what kind of nice properties does log norm function satisfy in generality? I mean, I write it here for PDN, actions of GLN, but what I'm saying will generalize. So how convex, in quotes, is our objective function, our log norm function for any given action? Surely it will depend on the action, right? If you have a very high degree action, it will probably not be as continuous as one that's linear, and so on and so forth. So here are some things that we know, okay, and sort of the idea is, we look at the toolbox of ordinary convex optimization, and we generalize the geodesic setting simply by saying something has geodesic property P if property P holds along all geodesics, okay. And in this present setting, it suffices to look at geodesics through the identity, so things that of the form e to the xt, okay. And so, for example, one thing that is true is that this objective function is geodesically smooth, okay. Meaning that second derivatives are not only, a convexity would mean they're lower bounded by 0, right? A Hessian is PSD. Here, the Hessian has the largest eigenvalue L, right? Or gradients are Lipschitz continuous if you want. Or another way to say it is that, along any geodesic e to the xt, or any geodesic of the form e to the xt, if I take second derivatives, this is upper bounded by some constant L times, and okay, now comes the norm square of x, because this norm of x kind of tells me, how fast I move along its geodesic. So unit speed would kind of mean norm of x equals 1, but of course there's sort of a natural scaling by the size of x here. So that's the geodesic version of smoothness, and it holds here, and the value of L depends on the action. Maybe we'll come back to it, maybe not. So that's one thing that's useful, right? So now we can immediately apply what I think Nicola told us on Monday. We can apply, the analysis for gradient descent and for smooth functions. Okay. It turns out that, okay, more is true, okay? So smoothness is great, but actually, what we care about, I presented to you this, this big picture at the beginning with lots of arrows and equivalences that I asserted. And I asserted to you that scaling and norm minimization, so norm minimization and gradient minimizations are equivalent. Now, to really, make this algorithmically equivalent, what I need to know is, if I'm close to the optimum in the primal problem in norm minimization, am I close to the optimum in the dual problem? That is my gradient small? And that's something that one can show. And one side is easy for some smoothness, the fact that gradient steps make progress. The other side is quite a bit harder. And so here's the result. Here's sort of the result that we could show, which kind of makes this old theory. I mean, this geodesic convexity goes back, to the late 70s. Makes it for the first time quantitative and usable in algorithms. And so what we're looking at here, right? We're looking here at the sort of the gap in the primal program. It's sort of a multiplicative one. So this is the minimum norm squared divided by the norm squared our current point v. Now this quantity is always less or equal to 1, right? It's close to 1 if you're close to the minimum. So if you could somehow say that this quantity is close to 1 if and only if the gradient is small, you would be happy, right? You would say, oh, my primal gap is small if and only if my dual gap is small. And that's exactly what's happening here, right? Because we see here that here we have the norm of the gradient divided by some constant, norm of the gradient squared divided by some constant. So if the gradient, is very small, the norm is close to how small it can be, and vice versa. Okay, so that's the content of these estimates, and they're of course extremely useful in actually analyzing algorithms. So what this shows, this resolves several puzzles perhaps that at once. So as we just discussed, it shows that normalization scaling are equivalent in a quantitative way. It also shows actually that one can solve the NALCON membership problem by solving either normalization or scaling. Okay, so for NALCON membership, I want to know is this capacity 0 or not. So what I could do is I could just try to minimize the gradient, for example, by doing gradient descent. And if I manage to make the gradient smaller than gamma, then this left-hand side is strictly larger than 0. So capacity cannot be 0. So I'm not in the NALCON. So this kind of reasoning can be pushed further to solve the NALCON problem. Yep.
So the absence of the square in the lower bound, is that somehow not removable? Is there's a fundamental reason for it?
Good question. It's something that has concerned us, but I don't remember now if there's some count example or not. Maybe I'll be up cold to remember. It's a good question.
I think it's necessary.
It's necessary?
Okay.
I mean, if it weren't there, I think we would have a lot better algorithms.
Okay.
Right.
So my
Right.
fundamental obstacle
Yeah,
is,
there is an
right?
obstacle.
Okay.
Okay. Thanks. Great. Okay. Yeah. So and the last thing I want to comment is, what this also shows is that in particular, scaling is possible if and only if you're not in the NALCON, right? What is scaling? The scaling problem. What was the scaling problem? Was setting gradients to 0, right? And setting gradient to 0, of course, can only happen if capacity is positive. Right? On the other hand, if capacity is positive, just go to the norm minimizer and the gradient will be 0. So that's these three statements together, they sort of resolve the maybe hopefully resolve this or they prove to you or they convince you that indeed all these problems we mentioned are related / equivalent in a precise quantitative way. Now these yeah. Yes.
Is there any known alternative way to obtaining this result, not relying on smoothness and complexity?
In the end, the way we prove it is in some sense by studying, the geometric programs you obtain by restricting your non-commutative group to all possible commutative subgroups. So in some sense, if you just make this change of variables e to the xt for any fixed x, you have a one-dimensional problem left in T. So I think that's good enough to roughly speaking prove these results. Although you do have to know a little bit about group action. So that's actually one point also with regards to a question that was in the previous talk, how groups and representations come in is sort of, gamma and L, they actually arise from group theoretic data. So if you have some concrete representation, you could possibly work them out, by hand or with a smart idea. But there's a very general recipe for how to compute these, these constants that arises. We can basically read off easily from the action. Is that?
Yeah. Thank you.
Does that? Okay. Yeah. So indeed, so L and gamma. So L is the smoothness constant, and gamma is another parameter. They depend on, if you want, combinatorial data of the action. I think I will not have time to talk about these. For those of you who know, they're related to what's called the weights of a representation. It's a bunch of integer vectors or points in a lattice that characterize representations of reductive groups. In some sense, yeah, maybe we'll come back to that later. You can ask me about it, but it's not so important. Point is, with any group, you can sort of associate some combinatorial data, a bunch of integer vectors or points in a lattice. And then with those points in lattice, there come things like what's the largest norm of these lattice points, what's the smallest, some convex hull of lattice points can go to 0, and these kind of gaps, they determine exactly the constants and this NC duality and this non-commutative duality statement. Okay. Okay, cool. So here's a summary of the first part, and well, a large part of the talk, I reckon. We call this non-commutative group optimization, but really what we're doing is indeed we're minimizing norms over group orbits for nice groups such as GLN, nice subgroups of GLN on finite dimensional vector spaces. We have this concept of a moment map, which is really just a gradient, right, at point V in the orbit through V. And this is part of the picture we already saw, right? The NALCON problem can be solved by doing norm minimization or scaling. scaling means setting the gradient to 0. Norm minimization means, well, minimizing norms. These are equivalent, on a sort of a non-quantitative, in a qualitative way by G convexity, and a quantitative way by these NC duality estimates that I showed you. And so this G convexity, so this underlying is the underlying, structure that might motivate why a simple greedy, sort of local algorithm can work with, rigorous guarantees. I mentioned that all these problems are now related in a quantitative way. So we really know, how small does this have to be in order to solve that problem, for example. Maybe I don't want to go into this too much at this point, but I guess we saw, various convex programming notions, appear when we discussed matrix scaling and the example of the Laurent polynomials. For example, I basically said in words things that amount to LP duality when I spoke about when the capacity is 0 or not. So in a sense, this theory, this framework can be regarded as a non-commutative generalization or a geodesic convex generalization of some of these things like LP duality and facts about geometric programs. And all the examples that Avi discussed, and also the ones that he had on his slides but did not discuss, basically fall into this framework in one way or another. So that's really nice. Okay, so now we could talk about what is really the class of groups for which we can carry out this theory. Maybe I'll just tell you what it is to sort of satisfy your curiosity, but not why it works. So the set of groups is basically, here's a concrete description. So they're called complex reductive groups. They're basically subgroups of GLN that are defined by polynomial equations. For example, SLN is defined by the polynomial equation determinant equals 1 inside GLN. And we want this group to be closed under taking adjoints. So, Hermitian conjugates are again in the group. If you have this, then basically everything I wrote before works very concretely. And the analog of passing from GLN to the positive definite matrices is now passing from this group G to the positive definite matrix inside this group. And that turns out to be in this generality a Hadamard manifold, or symmetric space of non-compact type. So what this is a Riemann manifold that has curvature, and the curvature is non-positive. So but has like a single coordinate chart e to the x like we saw before. So it's a very tame such manifold, but nevertheless it has non-positive curvature, which makes things challenging. Okay, but that's sort of maybe interlude for the experts. Now I think if I remember right when we started, I have maybe about 10 minutes left. So I want to talk a little bit about algorithms, and we'll see if we talk about polytopes. The good thing about with regards to talking about algorithms is that there's not so much to talk about, right? Because we already established all the technical basics. So for example, our function is smooth and has the smoothness parameter L. So clearly one thing we could do is we could run gradient descent with step size 1 over L, as was explained, I think on Monday. Okay. So so that's gradient descent, right? You have your current group element G that moves you from a starting vector to where you want to go. And you just update it, in this case, by left multiplying when you do a little step. And okay, here it's like a little geodesic step. So you use the exponential map and you to move along the direction of the gradient. And the gradient is, of course, the same as the moment map at the point where you currently are. That's how the moment map mu was defined. It's the gradient at point GB. Okay, so that's gradient descent. And one can show that for a vector that's not in the NALCON, and that's exactly when scaling is possible to arbitrary accuracy, gradient descent works. It finds a group element for any epsilon, finds a group element G, such that the gradient, the moment map at this point is epsilon small, and does so, as one expects in poly 1 over epsilon steps. And there's other dependence on the input size. Input size here means description of the group, of the representation of the input vector V. Everything except epsilon. Yeah. How does one analyze this? Well, the standard part is sort of the how to use smoothness in analyzing gradient descent. So it makes you trust gradients, right? And if you don't go too far, and you can combine this again. That gives you one bit, and then somehow there has to be something problem specific, and the problem specific part is a priori lower bounds in capacity. So if capacity is non-zero, one can show it's only exponentially small. And I'm not sure how we got around to saying this. I think he had it on his slides. This we obtain, and that's actually sort of the non-trivial input from again. So that's like a second input from group theory. And here we use constructive invariant theory to basically say. So basically, the idea is if you can construct invariants that are not too complicated, and they witness that our vector is not in the NALCON, then this can be obtained to obtain. Well, this can be used to obtain bounds on capacity, a priori bounds, and that's what's needed here. I explained before that we can solve the NALCON problem by choosing making the gradient small enough, namely smaller than gamma, this constant in the NC duality estimates. And so indeed, the same algorithm can solve the NALCON problem in time poly 1 over gamma and the input size. But now gamma is one of these combinatorial constants that depend on the action, simply by running gradient descent. Okay, and so the idea is, well, if you're not in the NALCON, then you can achieve this, right? If you just run gradient descent until you have this guarantee, right, that works by the theorem. But if you are in the NALCON, you can make your gradient never smaller than gamma by these NC duality estimates. Okay, so either way you win. So you just run gradient descent, and if you sort of assuming you are not in the NALCON, and then you check if your gradient is indeed below gamma. So that's the idea. So that's a first order algorithm. There's also a second order algorithm about which I'll be even more vague. So here the idea, so this is sort of the trust region or box constrained Newton method type. Here, what we do is we look at local quadratic approximations on some neighborhood where we can trust such a quadratic approximation. We have to regularize the objective, but okay, that's maybe a detail. And then if one does so, right, because the quadratic method, you can maybe hope for log 1 over epsilon convergence, and that's indeed the case. So we can show that if again we start with a vector that's not a NALCON, meaning the scaling problem is solvable for any epsilon, right? Or norm minimization has is possible to non-zero norm. Infimum capacity is non-zero. In this case, we get an additive approximation, epsilon additive approximation to the log capacity. So F is the log norm, right? So that's this log capacity. I should have written this. Within a number of steps is now log 1 epsilon, poly log 1 epsilon input size. But now again, this constant 1 over gamma creeps in. Okay. And so why is this? Well, how do you analyze that's the procedure for such a trust region method? Well, you have to know, what's the size of a region that you can trust, and you have to know the diameter of the sublevel set, a bound on the diameter of the sublevel set. The size of the neighborhood turns out to also depend on this quantity L, which I did not call weight norm, but I might have if I wouldn't have skipped this slide. So that was the thing that determines smoothness. It also determines what's called robustness in sort of recent optimization literature. And this a priori bound on the diameter we obtain in sort of a non-trivial way, but sadly we use NC duality along the way, so we pick up a 1 over gamma. Okay. So that's kind of what we get, and I guess I should say, okay, how should we feel about gamma? And how should we feel about L? For some reason, L never appeared in my time iteration bounds, right? Only gamma appeared at various points. And the reason is that L is harmless. It's usually polynomial in the input size, or it is polynomial in the input size. But this weight margin can be exponential, okay? And that really depends on the action. So it turns out that, for nice situations, like matrix, operator scaling, tensor scaling, where one dimension is fixed, certain quibbles and whatnot, gamma is only polylarge, and so we have polytime algorithms. But say for tensor scaling, or for non-uniform operator scaling, in case we don't get there anymore, actually gamma is exponentially large, and so that's a challenge. Okay, so basically these two algorithms I showed to you here, in some sense, the state of the art of what we know how to do. They subsume sort of previous work on, say, matrix operator scaling by alternate minimization. So these are not alternate minimization algorithms anymore. They do small steps, gradient steps, or the second order steps. They apply much more generally, of course, to G-convex optimization. The only way in which the problem enters is by diameter bounds and a priori bounds, capacity bounds, so on. And we can use either of them to solve normalization, scaling, or NALCON problems. And indeed, for many interesting actions, they are polytime, but not always, not in all parameters. So that's sort of a big open problem. Okay, so I'm not sure if we started like 5 minutes late. So if I may, I would still maybe keep going for 5 minutes. Cole, do you allow?
I allow.
Fantastic. I guess people can vote with their feet. Yeah, so maybe I'll be pretty quick. So maybe I just want to tell you where these what's the deal with these polytopes, right? I mean, they seem to be tantalizing. I mean, everyone likes polytopes. Okay, so let's just go back to the scaling problem real quick. So what does the scaling problem ask us to do? It says, given a vector, find a group element such that the gradient is almost zero. And gradient almost zero, or gradient equals to zero, right? That means, depending on the context, depending on the group action, doubly stochastic, matrix, an isotropic frame, a quantum doubly stochastic, quantum operator, in the case operator scaling, with these like m star m equals identity, m sum over m star equals identity, or uniform marginals in some more general settings. So kind of mu equals 0 in various contexts or various actions, means kind of uniform aspects, isotropic aspects, balancing. Okay. Now, in general, we don't only care about uniform marginals, right? So for example, for matrix scaling, we also care about RC matrix scaling, where where we prescribe row sums and column sums that are not uniform. And we might ask this problem in general. We might say, given a vector and a target marginal p, a target p, find a group element such that our gradient, our moment map, at that point is close to p, and p need not be 0. Okay. And we could systematize this by defining an object delta of v that captures all of these possible marginals, if you want, that I can obtain. So this looks very abstract, but for example, in the case of matrix scaling, what I'm saying here, delta is simply the set of all R, C of all row sums and column sums that can be obtained by scaling a fixed given matrix. Similarly for operator scaling, similarly in other settings. Okay. Now, if our group is commutative and we are in this Laurent polynomial setting, we saw before that gradients, or the set of gradients or the moment map sweeps out the Newton polytope. Okay. So a commutative setting is very simple. We simply get Newton polytopes in various disguises, in particular a convex polytope. What's rather amazing is that even for non-commutative group actions in the generality we discussed, one still gets convex polytopes by a slight twist of this definition. Instead of, maybe I'll say that, if you ask me about it. So a slight twist of the definition basically says that, this image of the set of all possible gradients in the orbit closure is basically thus sweeps out an Euclidean convex polytope, even though the underlying geometry is G convex, right? So that's super weird and quite magical. Okay. And what's funny is that these polytopes, they're usually quite complicated. So they may have exponentially many vertices or facets. And in particular, we don't know these vertices or facets without thinking hard and doing difficult math, even though the representation is on a polynomially large space. Okay. And so that's, of course, concerning on the one hand side, but it's also very cool, right? Because it allows you possibly to reason about exponentially complicated objects, by a polynomial time algorithm in polynomial space. So it's almost succinctly encoded. Okay, so there's lots of examples. One matrix scaling I already mentioned. So one of these moments. So this thing is called a moment polytope, and it's basically the set of all values that the moment map can attain. So one example I mentioned, matrix scaling. In this case, it's the set of row and column sums that kind of rise from scaling a fixed matrix M. Another example of a polytope that everyone knows is the Schur-Horn one. So if you ask, suppose I have a Hermitian matrix with fixed eigenvalues, what are the possible diagonal entries that such a matrix can have? So that turns out to be the convex permutohedron of lambda. And I think Nishit or Jonathan will talk about it actually from a very different perspective, but it's the same thing. And you could try proving the result, or you could try characterizing this with everything I've told you so far. You should be able to derive this result. And here's one non-trivial setting. Maybe I'll open those in case you want to glance, but one non-trivial example is following. Suppose you look at triples of Hermitian matrices A, B, and C such that A plus B equals C. Okay. And suppose you're interested in what are the possible eigenvalues of A, B, and C. So what is the eigenvalue of A, eigenvalue of B, eigenvalue of C, such that for any triple of matrices, such that A plus B equals C, Hermitian matrices. Okay. So that's some subset of R to the 3n, which has no reason to be a convex polytope. It is a convex polytope. Again, it's connected to lots of beautiful mathematics. So it's connected. I mean, that's basically the famous Horn's, formerly Horn's conjecture, now theorem, I guess, of Knudsen Tau, establishes, certain linear inequalities that describe this problem. And it's very tantalizing also from an algorithmic point of view, because we can decide membership in polytime due to a result by Kittan-Malmoley, which is very non-trivial. But how to actually find preimages, so solving this non-uniform scaling problem, or even solving the non-uniform scaling problem is actually quite tricky. And I mean, Cole has a beautiful algorithm, which is not yet polytime in all parameters. So basically, in non-commutative setting, we are sort of happy because they are really cool and interesting and not very well understood polytopes, but sad because the algorithms are not quite there. Okay, so I'll not tell you how we can do that, but one can reduce to norm minimization by some clever trick or twist. But let me just wrap up. So I guess I tried to tell you about three things. I think I only managed to tell you about 2.5, but maybe that's okay. So the first message of this talk, right, was sort explaining the unreasonable effectiveness of alternative minimization, right? And the key to explaining it is this geodesic convexity of the norm or even log norm function. And that holds for very general group actions, right? General reductive groups, and basically no assumption on the action. Okay. And observing, this underlying structure, this underlying explanation is then also key, and as you saw, right, to finding general algorithms that can then be based on, general principles of geodesic convex optimization. Okay. And so that's right why it's, interesting to see these hidden symmetries, to figure out what's the right geometry, so that then, we can tackle those problems beyond the domain of applicability of alternative minimization. The second message was that gradients are cool. I mean, gradients here are not just a thing that you use when you minimize an objective function, the directions that you pick, but they have intrinsic meaning. They capture natural scaling or marginal problems involving your joint distribution matrices, quantum states, frames, and so on and so forth. And then the set of possible marginals we saw very quickly, probably too quickly, can be encoded by actually Euclidean convex polytopes, so things like this, so-called moment polytopes. And they are cool because they're exponentially complicated if you look at them naively in terms of their description by vertices or facets. But sometimes we can probe them efficiently using algorithms. Okay, and we wish to do that in a more general context. Okay, so there's lots of things we don't understand. We don't have polytime algorithms in all parameters, all actions. Part of the reason is because G-convex optimization non-positive curvature, is still lacking compared to the Euclidean setting. We discussed this NALCON problem, which we can now tackle here. But this NALCON problem is one, out of like a whole array of interesting computation problems in invariant theory. What about those? And there's first results for various actions. Can we sort of do better? Can we systematize those? And more generally, of course, how can we tackle other interesting problems? Maybe the commutative PIT problem that offsets its symmetries. Yeah. So thanks for your attention, and sorry for running over time and even speaking to you online. Thanks.
Any other questions? Okay.
So if you take a vector v and in this orbit that you consider if 0 is not there, is there any interpretation of the minimizing point in terms of those invariant polynomials?
Yeah. So basically, if you take, say, a homogeneous polynomial, right? So the homogeneous polynomial would be 0 at the 0 point, and you take one that's non-zero, right? So yeah. So if you have such a situation like in the picture here, right? You know that you can separate this orbit from 0 by an invariant polynomial. Let's take it to homogeneous, so it's 0 here and non-zero on this orbit. I think it's basically maximized. It's basically exponentially concentrated on the point of minimal norm. Yeah. So it's like where the invariant has largest absolute value, or a invariant, yeah, that witnesses the separation.
Yeah. So I have multiple answers. I'll start. The first one is so when you started with like fix v, fix p, and you said for all given v, what are the p's that I can achieve, right? And that was the moment polytope. What Avi talked about was the dual question, which is you fix p, which in this case was uniform marginals, and tell us that permanent larger than strictly positive permanent showed that v was like matrices with strictly positive permanence could get you there using scaling. So I wonder, do we know anything about the pre-images of a particular P? So you give me P, and I ask you what are the V's that can actually get there by scaling?
I mean, maybe let me make sure I understand. So what Avi said, right, is sort of he told you if the permanent is non-zero, then you could scale to, say, uniform marginals, right, to a fixed P. That's what you said, right? Yeah. So the permanent here in this setting you could think of as an invariant polynomial in some sense, right? I mean, we plug in these positive matrices, but something that doesn't change under scaling by determinant one matrices. So the generalization of that statement would be something like if you have an invariant polynomial that's such that P of V is not equal to P of 0, so it separates 0 from the orbit, then you can scale to uniform marginals. So that's the generalization of that statement. Okay. So the other question I think you asked, right, is sort of, can we characterize those vectors for which the moment map is 0, right? So
Asking
yeah,
about
so
other P.
I said, like, if you give me, if I give you P's, I
oh
give
yeah,
you
I see.
sets of marginals, let's say in the Sinkhorn setup, and I ask you.
I see. You wanna like know what sort of the analog of, say, a permanent for RC scaling or something like that.
That's right.
That's right. Yeah. So in complete generality, basically one has to replace invariant polynomials by polynomials that transform in a certain way. So sometimes people call them covariants. So I'm slightly lying, but maybe that makes sense to you. So rather than not changing, so not changing at all kind of corresponds to the 0 point, and so to moment map equals 0, and changing in sort of a controlled way. Say say you apply your group element, and then what happens is your function does not stay invariant, but it actually changes like a determinant. So but that's a scalar, right? Then that will correspond, for example, to scaling to all ones marginals. So and for interesting points, if you really want to scale to margins that are really, I don't know, like 5, 7, 2, 1, then 5, 7, 2, 1, I guess 7, 5, 2, 1, which would be, say, your row sums, would label would label a certain representation of your group if you want. And you kind of you are looking for a polynomial or a bunch of polynomials that transforms in this way. So it's not invariant, but it's transforms in a controlled way, and then and only then can you solve the scaling problem. So yeah, probably that would have been much nicer to write on a whiteboard. But that's maybe that's kind of the general answer here.
All right, thank you.
So basically all points in this polytope of possible marginals, they are characterized by kind of covariant polynomials. So and the origin corresponds to invariance polynomials.
You got a question?
And the original, yeah.
Yeah, I had a question. First question was, you were talking about how you can use the time discretization of the gradient flow, either a first order or a second order, to design these algorithms. And my question was, did you consider any implicit time discretizations, or what was the reasoning behind choosing an explicit one, for example, for the first order one?
I think just naivety. I mean, it's something that we knew how to do. Speaking of gradient flows, I mean, I think that doesn't maybe fully address your question, but it comes to mind as maybe interesting to say. Actually, when we prove these diameter bounds or these diameter bounds and related things and bounds and capacities that we actually need to make gradient descent effective, we do actually study the continuous gradient flow to sort of numeric, sort of analytically, sort of by hand, to get these bounds. So maybe that's interesting. But that would be then fully continuous time though. But yeah, I mean, I would say sort of other algorithmic schemes, maybe mostly our naivety starting with a simple scheme. Interesting.
I have a few more questions. One is,
Sure.
You consider other geometries, taking the gradient with respect to other geometries. Are there any others that you know of that would be natural to think of in this context? Other geometries for the same objective function.
So it's always, so the general setting is, you take some nice subgroup of GLN, that's closed under Hermitian adjoints, and then you look at the positive definite matrices in this group. So these are always going to be generalizations of PD matrices. But for example, it could be, if your group action is by SLN, then it would be determinant 1 PD matrices. Right? And that makes it already clear that we should not look at the Euclidean geometry of the positive definite matrices, because if we set determinant 1, it's no longer a Euclidean convex set, right? But that, I guess maybe that's still not so interesting to you. I guess you're looking maybe at for groups that are not of the GLN, SLN type. There, I have to say, personally, the only example that I know are certain symplectic groups. And then there's also sort of the PD elements in it that one can study. But somewhat in general, these are always, they have a very similar flavor, I think. Like they're always non-positively curved manifolds, with a single coordinate chart, so it's a Hadamard manifolds, and they are classified if you want, so it turns out that the set of groups that I mentioned before, even though it looked very flexible, arbitrary subgroups defined by Tome equations, closed and taking adjoints, actually you can classify those completely, and therefore, there's also then a classification of these spaces, these geometries that appear naturally in the setup. So, for example, a group that we would not would not necessarily know how to optimize over, I guess. One can imagine, for example, group of upper triangular matrices acting in a way that does not extend to some, to all of GLM. And that may have a different flavor. And I don't know, or that may have a different flavor. But somehow, yeah, for us, it's always sort of totally geodesic submanifolds of PDN, basically. Maybe that's a good way of saying it.
Yeah, and sorry, I'll just ask one more. Other types of norms. You talked about the two Frobenius, other functionals that you might consider to optimize with respect to the same geometric structure.
Great question. Yeah, I mean, I don't have anything to report, although there are interesting things we're thinking about. But somehow here, yeah, so far what I showed seemed pretty kind of married to the L2 norm, because we had some of the L2 norm was so. I mean, some of the reason why I ended up in PDN, was I could get rid of the unitaries, and the unitary sort of the unitaries in my group, they would act in a way that preserves the L2 norm. So that's by unitaries. So unitaries get mapped to unitaries. So that's kind of nicely canonical. I'm not sure, say, doing something like L1 or how that would fit in, but it's an interesting question. We've thought about some other functionals which are maybe not of the norm type, which may appear here. But yeah, I don't think I have a good answer or some concrete proposal.
Thank you.
Thanks.
Any further questions? All right, let's thank Michael.
Hey, thanks very much.